Good morning, good afternoon, good evening, whenever you happen to be watching this video. Tanya Laird here, and this is part 1 of Lecture 6 of ENGR 231 Engineering Statics. In Lecture 6, we are going to be exploring engineering couples, and this video is going to be divided into 3 parts. In the first part, we're going to discuss exactly what a couple is. In the second part, we're going to learn how to calculate them, or how to calculate the moment produced by them, I should say. And in the third part, we're going to discuss equivalent force couple systems. So the topic du jour, the topic of the day, is couples. Now, if I ask the average person on the street what a couple is, they're probably going to tell me something, oh, well, we can probably imagine something in the realm of interpersonal human relationships. But that's really not what we're getting at here. That's definitely an interesting thing to explore, but not really something we're interested in engineering statics class. Most human relationships tend to be non-static, but engineering jokes. Okay, usually not very good. Okay, so let's see, couples. So again, we need to learn a few things. First, what are they? Second, calculating their moments, or calculating moments produced by them. And then 3, we need to look at, of course, looking at equivalent force couple systems. Equivalent force couple systems. And these are going to be in parts 1, 2, and 3 of the lecture, which will be their own separate videos. Okay, so first let's get right into this, looking at what couples are. What is a couple? What is an engineering couple? Or what is a couple in this context of statics class? So what is a couple? Well, to explain this, I first need to review a bit of what we have looked at previously. And previously we spent a lot of time talking about moments, and so really a couple is a condition of forces that produces a very special case of moment. So we know that if you have a 3-dimensional system or a 2-dimensional system, doesn't really matter. Maybe I'll draw out one of each. X, Y, and Z. And then maybe just a simple 2D case as well. Like so. X and Y. If you draw this, so let's say we have a force, or in order to have a moment, we're going to need 2 things. Maybe I'll do my forces in red. Generally, we're going to have a force, some sort of force vector. 2D, 3D, doesn't matter. We'll have a force vector. Let's say for each of these I was looking at the moment about the origin. Let's say I was looking about at the moment about the origin, maybe here. Maybe this is R. I'll call this one R1, and this one R1 for the 2D case. I'm not going to be doing any calculations here, so we can call these both R1. And then let's create another point called, oh, I don't know, maybe point A. Point A, and point A for the 2D as well. And then going there would be an RA. Just 2 different displacement vectors for each of these. You know, I wouldn't actually have to go to the same point, but to be consistent, I'll just go ahead and show them going to that same point. RA here. So we know previously that for both of these, that RA, considering our RA, or the moment about A, I should say, the moment of this force about A, is going to be equal to RA, the vector RA, crossed into F. No great surprise there, R cross F, and that's the moment about a point, not the moment about an axis, of course. And the moment about the origin, as we've labeled this here, is going to be equal to R1 cross F. Fairly straightforward, just taking the 2 displacement vectors and doing the cross product. But the real important thing here is that these are not equal to one another. RA cross F is not equal to R1 cross F. It's the same force vector, but it's going to be a very different displacement vector. So for regular moments, the displacement vector matters. The displacement vector, or in particular, more properly said, the moment arm matters. Or moment arm matters. In other words, depending on where I take the moment about, I'm going to get very different results. So if I take the moment about over here, I'm going to get a different moment than if I take the moment here. I'm going to get a different moment than if I take the moment here, etc., etc., etc. Everywhere I take the moment, I'm going to get a different result for the final value of the moment and for the final moment vector. If I have the same distance, maybe if I went equal and opposite along here, I would get the same magnitude of moment but opposite direction. But again, for normal moments, depending on where I take the moment vector, or depending on where I take moments about, I will get different moment vectors as a result. Now, we do remember from our previous discussion of moments that I can take this displacement vector from the point that I'm considering to anywhere along that force's line of action, and it will be the same. However, it has to go from that point and to somewhere along that force's line of action. The moment I move, or the instant I move that point, then that moment will be a different. The moment produced by that force will be different. And if I want to look at a very intuitive example, we can see this through something very simple. We discussed a door previously, but if you want to look at something even simpler, you could imagine something like a simple example. Consider a simple example a bolt and a wrench. If I have a bolt, simple hexagonal bolt here, and I'm going to attach to it a crudely drawn wrench, extremely crudely drawn wrench, as you shall see. Oh man, this is going to be really bad. Wow. It looks like a tuning fork. Wow. Okay. Anyway, thankfully I'm not in the tool manufacturing business. So wonderfully crudely drawn wrench here. Very spindly little handle too. So in order to turn a nut or to turn a bolt, I need a certain amount of torque. I need a certain amount of moment produced. And if I have a constant force, let's say I apply a 10-pound force here versus a 10-pound force here. If you've ever changed a nut on a tire, changed a tire on a car, you know that of course you have to take all the bolts off, you have to remove the tire, blah 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 blah, yada yada, etc. etc. But you know that where you place the force on the wrench, depending on where you place the force on the wrench, you will get a different result. So if you're now do this properly, probably if I want to show this being taken off, I'd have to show the forces being applied in the other direction. But if I want to loosen the nut, or if let's say I want to tighten the nut, I'm going to have a lot easier time tightening it if I'm applying a force here than I am over here. And that's because I have a longer moment arm. Very simple, very long lever arm. Or if I'm loosening it, there's actually a minimum amount of force required to even get it moving, because we got to overcome the internal friction in the threads of the bolt here. And so if I want to, and that friction is represented by a minimum moment, or later we'll see a minimum couple. And but think of it as a minimum torque that is required to turn this bolt, and that you need that to overcome the internal friction, maybe some rust that's built up on the surface of the threads, whatever it may be. And that force can be quite substantial, or that moment can be quite substantial, especially if that nut hasn't been, and that bolt hasn't been moved in a while, because that might be a little rusted or something like that. And and if you've ever done this before, you'll know that the longer the wrench you're using, the easier it is to take this off. And in fact, sometimes what you can do is you might actually want to use, if you find yourself unable to unable to turn a nut, you can actually use what's called a cheater pipe, which you could put a big long pipe on the end of this thing. And if you're not able to generate enough force, you can give yourself a little bit extra moment arm and open it that way. Of course, you do have to be careful because cheater pipes, they can be good in small doses, but you got to be very careful with that because you might think, oh, if a 1-foot cheater pipe is good, a 15-foot long cheater pipe will be even better. And if you put some ridiculously long moment arm onto the end of a wrench, well, if you try to turn the bolt that way, you may apply so much moment that you're, well, looking at it in profile, the bolt is going to look like this. It will look something like this. The thread's there, and with the head of the bolt here. And there, especially if there's a lot of friction or a lot of rust built up in here, if you just apply a monstrously large moment here or a torque here, especially if you apply it very quickly, you might just shear that thing right off, and then you have a bolt stuck in your tire and stuck in the threads of your tire, and you're going to have a very hard time getting that out. You're going to have to take that to a shop and have that drilled out, and they're going to make you, or you're going to make them very happy because you just made them a whole bunch of money, but they'll happily charge you a whole bunch of money while laughing at you for using your 15-foot long cheater pipe. But that's neither here nor there. The point is that for normal moments, distance matters. And in particular, distance from the point matters. That's what I'm really trying to get at in my long rant here. Distance from the point matters. Whatever point you're taking, the distance absolutely matters. And the reason I bring up the wrench example is because here's a fixed point that we have to take the moment about, the wrench, and if we extend the force out, well then if that changes the distance to that point. Now, couples are something that are a little bit different than this. Couples are a special case of moment produced with a particular arrangement of forces. And there are a few definitions of couples, and I can define couples a few different ways. So the first one I could define a couple as is perhaps a free moment. A couple is a way of defining a moment or producing a moment that it doesn't matter where you sum moments about. So this is perhaps the most generic definition of a couple. It is a free moment. So it does not matter where you apply it. It's a free vector. Where on an object is applied, the same moment will be produced, or the same tendency to rotate will be produced. So that's one way to define it. And so these are just, what I'm going through here is a variety of definitions, and a couple is all of these things, and these are all compatible with each other. 2 is pure liberated rotation. And this applies to the free moment. So maybe I'll draw these out again. So pure liberated rotation. This is where a couple produces no tendency to rotate. Or sorry, no tendency to translate. Normally, when you apply force to a body, it will have a tendency to translate and rotate. But with couples, it only creates a tendency to rotate. No translation tendency is created. Only a tendency to rotate. So let's draw out a generic potato body here, maybe with a center of mass somewhere here. And let me define points A, B, and C. So let's define those. And maybe I have let me apply a couple of 10 kip inches. 10 kip inches, and 10 kip inches. In free body diagrams, this is how we show a couple being applied to a body. We don't draw a straight line force, we kind of just draw a curving or rotating arrow. And because it's a curving arrow like that, and because it's labeled in kip inches, I am showing that I am basically applying pure moment to the body. And also in turn with this, it doesn't matter where this is applied. So if I had only this 10 kip inch moment or this 10 kip inch couple applied at point A, it would experience the exact same tendency to rotate as if that was applied at B or if that was applied at C. Or if all three of them were applied to the body, it would be exactly the equivalent, or the object would behave exactly the same if there were a 30 kip inch couple applied at B, or a 30 kip inch couple applied at C, or a 30 kip inch couple applied at A. It is basically a way of applying pure, distilled, liberated rotational tendency to a body. And by rotational tendency, I mean, of course, that if this thing were floating in space, it would start to accelerate, and it would start to turn. It would start to rotate about its axis. And again, if I apply a couple to a body, it doesn't matter where I apply it. I can apply it here, 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 or here, basically. It doesn't matter where I apply it. It would start rotating with the exact same, say, radians per second squared angular revolution. Angular rate of acceleration, I should say. Again, it is a pure, liberated rotational tendency. So that's all well and good. That is the ideal version of what a couple is. But how do you actually produce it? So this is really what I think of a couple as. I'm going to give you another more direct example or direct explanation of how to create it. But in my mind, this is what a couple really is. When I think couples, I think at a high level kind of, they are pure liberated rotation. And so now how to actually do that, it will discuss later or in the next slide, the next couple slides. But really, that is what a couple fundamentally is. At its deepest level, a couple is pure distilled rotation. It is anything that, basically, I think of anything that causes pure rotation on a body that somehow causes pure rotation on a body to be a couple. But really, there's only one way to directly do that, as we'll see here. So another way to think of it is a particular arrangement of forces. So here's how you actually produce, how you actually mechanically produce a couple. So these forces need to be two things. One, they need to be equal in magnitude and opposite in direction. You need two forces. They need to be two forces, A, equal in magnitude, and B, opposite in direction. Now, if these were applied at the same point, they would simply cancel each other out. However, actually, let's go ahead and put these, maybe A, B, and C, separated by a certain distance. That is really the key. Separated by a certain distance. So if I have two forces that are equal and opposite and applied at the same point, say something like this, F and F, two force vectors, if I apply them at the same point, they're just going to cancel each other out and just go away. However, what if I have a rigid body, or just something that I can apply two forces in an opposite direction separated by a distance, then something really cool happens. This is where we get our pure liberated rotation. So if I have one force vector here and another force vector here, again, they're basically parallel but in opposite directions. Another force vector here, but separated by a certain distance. Separated by a certain distance d. This is where I get a couple. And the magnitude of the couple is going to be equal to m equals f, the magnitude of f, the magnitude of the force vector, times the distance d. So the magnitude of the couple is going to be equal to the magnitude of the force vector times that distance d. And that's how we can get this mathematically, but let's look at how this is actually produced. And I'm going to demonstrate this using a simple 2D case, but if you wanted to work through the 3D case as well, using some generic moments in terms of variables, you could also do this. So let's look at let's consider, for example, a simple, again, I'm going to work through a very simple case to illustrate how this can occur. And again, I'm going to work through, I want to keep this relatively brief. So I want to show what would happen if you have something like this. Let's say we had a force. Let's consider two different forces, well, equal and opposite forces. Let's say we had a 10 Newton force and a 10 Newton force. And, 10 Newton force there. And let's consider a few dimensions. Let's say this dimension is 5 meters, and then between the two is 5 meters, then to the origin is 5 meters, and then down to some point, let's call this point, point A is also 5 meters. So 5 meters, 5 meters, 5 meters. 5 meters between the forces, 5 meters down to the origin, and another 5 meters down to point A. So I want to see what happens when we take the moment of these two forces about the origin and the moment about point A and see if we get the same result. Because again, if it is a pure, if a couple is a pure liberated rotation, or if it's a free vector, it shouldn't matter where we take moments about, we should get the same result. And I'm doing this as a very simple example with very simple multiplication, but the same thing works whether these are tilted at an angle or whether it's a three-dimensional case, whatever it may be. So let's first do a moment about the origin. I do like this simple case because it really illustrates with relatively simple math how this works out. The same would work in 3D cases with cross products and such, but it's a little bit more, it's a little less intuitive to see. So the sum of moments about the origin, I'm going to have, let's see, well, this 10 Newton force is going to produce a positive moment, 10 newtons, and then its moment arm length is going to be 10 meters. Then this 10 Newton force here will produce a negative moment, minus 10 newtons, with a moment arm length of 5 meters. So we have 100 Newton meters minus, I missed my 5, minus 5 meters, so minus 50 Newton meters. And that will come to a total of 50 Newton meters. And what do you know? That is equal to the magnitude of the force times the distance between them. Or if I took a sum of moments about point A, the same thing would occur. I could have the 10 Newton force, this time times a moment arm length of 15 meters, and then the minus 10 Newton, or the negative moment produced by the bottom force, minus 10 newtons times a moment arm length, this time of 10 meters, and I will get 150 Newton meters, minus 100 Newton meters this time, and I will get a total moment of 50 Newton meters. Now, also look for both of these. What happens if I do a sum of forces? In the y direction there would be no force, but if I do a sum of forces in the x direction, I have negative 10 newtons, and then plus 10 newtons, and this would simply come to 0. So notice, these two forces will cancel each other out in terms of their tendency to translate, but regardless of where we sum moments about, they'll produce the same tendency to rotate. And I did this in terms of dimensions, but we could do the same thing in terms of variables. The entire idea is that regardless of where you sum moments about, the actual distance to the first set, the first force here, is going to cancel out because they both have that same component of the moment arm. And the only part that doesn't cancel out is the moment here, is the distance between them. Another way to think of this in 3 dimensions, if I want to think about this in 3 dimensions, if I have two forces, equal and opposite, F and F, we know that if we take the, we know from previous discussions of moments that we can take the moment anywhere along the force's line of action. I can take, if I'm looking at the moment about the origin, I can take the moment here, here, here. It doesn't matter. I can do that at any point, and all that will remain, or not all that will remain, but I can take it at any point along the force's line of action, and the moment will be the same. So why not take it from the perpendicular distance? So again, I can choose an r vector here, say an r1, that is perpendicular, and an r2 that is perpendicular, plus and there'd be the d here, separation. Basically, I would have r1 is equal to, well, the magnitude of r1, well, actually I can say r1 is equal to r2 plus the displacement vector here. R1 is equal to, actually, the other way around, sorry about that. R2 is equal to R1 plus the distance between them, the vector describing the distance between them. And if I take moments, I will find, again, because these are simply multiplications. These are going to be simple multiplications because this is a perpendicular distance. Because R1 and R2 are perpendicular to the forces, to the force vectors, the moments will simply be the magnitude of each of these. Will simply be, I could say, m2 would equal the magnitude of f times the magnitude of the r, and then m1 would be the same. Magnitude of f times the magnitude of r, actually I should put a 2 here and a 1 here, times the magnitude of r1. And again, because they're going to have that, because everything is aligned here, if I take the moments of the origin of this, in R2's case, the part of it that overlaps of R1, that portion of the moment arm will cancel out, and the only part that will be left over is that D. So only the moment produced by the distance between the vectors is not canceled out. By D, the D vector remains, and that by R1 cancels out. Again, finally, we can think of this as basically the distance is just a little bit extra of the moment arm. And when we take the moment produced by this, but again, because these are all aligned perpendicular, if everything's nice and, well, actually all of the radiuses here would be parallel to each other, and the distance here would be parallel as well. And because these, the displacement vectors, as I've defined them, are perpendicular to the forces, the actual moment, even when I do the moment of the far force, the one with the R2, the only part of that moment that's going to remain is the part that's created by the distance from this one to this one. And that's what we have seen here. And so fundamentally, that's what a couple is. We look at, in the second portion of the lecture, the second video, we will look at how to calculate some of these mathematically. We will look at calculating couples and seeing how we find moments produced by them in 3 dimensions. But really, ultimately, it's not too bad. This is the basic idea of a moment, or sorry, the basic idea of a couple. It is again, a liberated moment, or a liberated rotation, a pure rotation. When you apply it to a body, it doesn't matter where you apply it to a body, it will produce the same tendency to rotate regardless of where on that object you apply it to. And it's produced fundamentally by having 2 forces that are equal in magnitude, opposite in direction, and separated by a certain distance. You need all 3 if you're creating couples via forces, by the direct application of forces. You need all 3 of these things, but if you do that, you'll get a very particular and special case of moment, and that is a couple. All right, that'll do it for this portion of the lecture. I will see you all in part 2, and as always, thank you.